Water exits from a circular pipe 10 centimeters in diameter with a mass flow rate of 4 kilograms per second and strikes a flat plate at 90 degrees. The velocity at the exit varies linearly from a maximum at the pipe center line to 0 at the pipe wall as shown. Determine the force exerted on the flat plate. Compare this to the force that would be exerted at the same mass flow rate if the pipe exit velocity had been uniform. So here we have the pipe, here we have the water coming out of the end of the pipe, and it's splashing into this flat plate, so it's going to be deflected into the vertical plane. And notice it's a non-uniform velocity profile. So it says the velocity at the exit varies linearly from a maximum at the pipe center line, so that's right there, to 0 at the pipe wall, so that's right there. So this is an axisymmetric profile. Remember, the pipe wall gives 0 velocity there, and again that shows up down here. So our given information is the diagram that's been shown here, and we'll be adding some detail to this as we go through our solution. What have we been asked to find? Take a look at the problem statement again. Determine the force exerted on the flat plate and compare that to the force that would be exerted if the velocity had been uniform. Okay, so part A, we find the force on the plate, and in part B, we redo for uniform velocity profile. So that's what we're after. Assumptions. Again, we'll leave that blank and fill it in as we make it. And our analysis. So back up to the diagram here to talk about the analysis. So we're trying to find a force in this problem. And it's obviously not a fluid statics problem, but we're trying to find a force. So we want to use conservation of linear momentum, because linear momentum talks about forces and the resulting change in momentum. So that's what we're going to do. So it's a control volume analysis. So we want to begin the discussion here by showing our control volume. So the control surface that we want to choose is going to cut right through this jet right at the exit, and then it's going to include the flat plate. So this is the control surface that I'm drawing here. So when we pull out the linear momentum equation, we're going to be looking very carefully at how it applies to that control volume. So that's the control volume. The other thing I want on here is a coordinate system. So I'm going to put that direction, I'm going to make X, and this direction I'm going to make R. So that's a radial direction. Remember, this is a circular pipe, and so this is an axisymmetric velocity profile. So I want X to be my axis along the center line of the pipe, and R to be a radial coordinate, or distance away from the center line. So that's what we're going to. So make notes about that down here. Establish control volume. And that's done on the diagram. And establish a coordinate system. And that's also done on the diagram. So now we can begin with our conservation of linear momentum equation. And we always want to start with the complete equation. Think about each term in the equation, whether it applies to this problem or not. So conservation of linear momentum starts off with a body force. So we have density times g times dv, that's the body force, minus pressure forces on the surface, so P N dA over the surface, plus viscous forces, plus reaction force. So those are all the forces on the left-hand side of the equation, and those give rise, potentially, to some rate of change of the momentum in the control volume. So that's rho v dv, plus some difference in the momentum as it flows over the surface. So that's an integral over the surface of rho v r dot n dA. So that's our complete linear momentum equation. So now we want to start thinking about all of the terms in that equation and how it applies to this problem. So the first one is the body force term. So if we go back up to our problem statement and our diagram, that is the weight of everything inside of this control volume. So if we take a look at what's in the control volume, well, there's some water in there, certainly, splashing against that thing. There's some air in there, certainly. And there's also this deflector plate and part of the strut holding it in place. So there's all kinds of things inside of the control volume. Now, we really don't know anything about the mass of this deflector plate. So we certainly can't come up with a number for the mass of that thing. We also really don't know how much water there is in here either. Look at. So we've got a coordinate system and a control volume chosen. So what we're going to do here is neglect the body force. And there's a couple of reasons for that. First of all, we don't have enough information to calculate what the body force is. But secondly, it really doesn't affect this answer that we're looking for. We're trying to find the force exerted on the flat plate. Okay? So the force that this fluid exerts on the plate. So as we're going to see in a moment, we're going to come up with that by solving for this reaction force down here. So if we solve for this reaction force, neglecting these body forces, then we'll just get the effect of the water splashing on it, and not the effect of this having to support the weight of this thing as well. So that's our first assumption that we're going to make, is neglect body forces. And as far as the equation is concerned, that term goes. Next are the pressure forces. So what we want to do every time is go back to our control volume and take a look at our control surface. Because remember, that's an integral over the surface. So we want to see what is the pressure on the surface of this control volume. Well, as we've talked about, anytime we have a free jet here, so water coming out of the end of a pipe, the pressure in that jet is just going to be atmospheric pressure. So the pressure everywhere on this control surface is atmospheric. And when that's true, when the pressure is the same everywhere around the control surface, then this term will evaluate to 0. So if that pressure is a constant everywhere, it comes outside, and that it evaluates to 0 because the pressure is pushing equally on all sides of our control volume. Next, viscous forces. So again, viscous forces are due to force produced by fluid shear on the control surface. So we're only again worried about what's happening on the surface. Well, here we have an inlet, of course. Water's flying in here, but the water is just moving perpendicular to the surface. It's not moving parallel to the surface, so it can't produce a shear force on the surface. So there's no viscous force here. The water, of course, is going to hit this deflector plate, and it's going to splash in all directions. So it's going to go up, it's going to go down, it's going to come towards us, and it's going to go into the screen as well. So it'll be spreading radially in all directions. So everywhere it crosses the control surface, it's going to be crossing perpendicular. So there's not going to be any shearing force on the control surface there either. So we can neglect shear forces. So no viscous shear. Notice it doesn't matter whether there's viscous shear on the surface of this plate. So as the fluid hits this and starts traveling in that direction, in this direction, there could well be shear on that plate, but that doesn't matter because that's inside the control volume. It's not on the control surface. And that's part of the magic of control volume analysis. You don't have to worry about what's going on inside. You just have to worry about what's happening on the surface. So this viscous force is gone. The reaction force is very important in this problem. Remember, that's the force in any solid object sliced or cut by our control volume. Well, that's happening right here. This strut or post holding that plate in place is cut by the control volume right there. So the reaction force is happening there, and we certainly need to keep that. Now moving over to the right-hand side of the equation, first of all we see the unsteady term here. Well, we're going to be assuming this is a steady problem, and so that unsteady term is gone. Now the last term we see here is the integral over the surface of the momentum flux. Well, one thing we always want to be thinking about at this point is, can we make the uniform flow assumption? Well, if we take a look at this inlet, we cannot make the uniform flow assumption. The properties, in particular the velocity of this fluid, are not uniform over the inlet area here. So we certainly can't make the uniform flow assumption there. So what we do is write down what is left of our equation for this particular problem. So the reaction forces are going to be integral over the surface of rho v Vr dot n dA. So now we need to take a look inside of this equation and figure out what this looks like. So first of all, notice this is an integral over the entire surface. Well, where on this surface is there flow across the control surface? Well, certainly there's flow at the inlet here, and there's also going to be flow out of the control surface radially in those directions there. Up, down, towards us, away from us, and at all angles around there. So the exit flow is sort of a radial sheet of water coming away from that plate. The inlet flow is all coming horizontally here from left to right. Now what we need before we can proceed much further here is an equation that tells us how the velocity here varies with position, and in particular how it varies with our radial coordinate. So that's the next thing we're going to do. So that we can evaluate this integral, we need to know how the velocity varies with position at that inlet. So let's take a look at that. So we need the velocity as a function of r. Okay, and it's a u component of velocity that we're looking at here because it's the velocity in the x direction. So we've been told that this function is linear. So the way I'm going to write this down to get started, uc will be the center line velocity times 1 minus r divided by r. So what is this? Well, uc is the center line velocity big R here is the radius of the pipe. So we're talking here about the velocity profile at the inlet. So let's go back and see what that looks like. We're getting an equation for this velocity. It's the u component of velocity as a function of r. Remember, r is the distance away from this center line. So if we take a look at the equation we've got, if we let r be the radius of the pipe, it should give us 0 velocity. So let's see if it does. Let r be the radius of the pipe, that becomes 1. 1 minus 1 is 0. So the velocity goes to 0 when that r equals the radius of the pipe. Likewise, on the center of the pipe, r is equal to 0, and this velocity should be the center line velocity. So let's see what happens there. When this r is 0, u is just the center line velocity. So that's where this came from. It's a linear relationship because u depends directly on r, and it evaluates to 0 at the pipe wall and uc at the center line. So that's good. So that's an equation that is going to go into here to tell us how the velocity varies with location on that inlet surface. Now the only problem with this is we don't know what this uc is. Okay, we do not have a number for that. What we are told about the flow coming out of here is that its mass flow rate is 4 kilograms per second. So we need to think about conservation of mass here a little bit in order to get that center line velocity, so we can return to our linear momentum equation and calculate the force in this reaction. So that's what we're going to do. So we need to get the center line velocity from the mass flow rate. Well, we're given a mass flow rate, And what that's equal to is the integral over that inlet surface. So I'm going to call that integral over the inlet of the density times Vr dot n dA. And the mass flow rate would actually be the magnitude of this, because at the inlet that will evaluate to a negative number. I'm just interested in the magnitude. So that's at the inlet. Well, what is Vr dot n? Well, we come back to our diagram here. The unit normal at that inlet looks like that. Okay, always projecting out of our control volume and into the surroundings, perpendicular to the control surface. Well, this velocity that I've been solving for is in the negative ni direction. Okay, so V dot n we actually already have. It's that equation right there. So V r dot n equals negative UR, which is equal to negative UC 1 minus R over R. So that's how V dot n varies with position R. So that's good. So now we can come back and assemble this. Mass flow rate. Remember what we're integrating with respect to here. This is a circular pipe, so our dA is going to be RD theta. So we'll fill in the limits in a moment. We have rho. We have UC 1 minus R over R times our element of area, R dr d theta. Limits of integration on R are 0 to capital R. Limits of integration on theta, 0 to 2 pi. So we're covering the entire circle. And notice this negative sign I've dropped because we've taken the absolute value of this. So this is going to allow us to find this UC. We know everything in this equation except UC. So first of all, we need to do the integration. Notice nothing in here depends on theta. So the theta integral evaluates right away just to 2 pi. We have the density is constant. UC is constant. So we're left with an integral from 0 to R of R minus R squared over R dr. Remember, there's this R here that has been distributed into this. So that's equal to 2 pi rho UC R squared over 2 minus R cubed over 3R evaluated from 0 to R. So the mass flow rate equals 2 pi rho UC R squared over 2 minus R squared over 3, or pi rho UC R squared over 3. So this relates the mass flow rate to that centerline velocity. So we can now calculate our centerline velocity. So U centerline will be equal to 3 m dot divided by rho pi r squared. So that's equal to 3. The mass flow rate was given as 4 kilograms per second. Density 1,000 kilograms per meter cubed. Pi times r squared, 0.05 meters squared. So the centerline velocity evaluates out to 1.528 meters per second. So we've looked at conservation of mass in order to get our centerline velocity. So now we're ready to go back to the linear momentum equation. Now, we want to talk a little bit about this equation before we start working with it. Notice right now it's still a vector equation. Reaction force and velocities in here that give it direction. Back up to the diagram here. Notice that the reaction force on this thing is going to be purely in the x direction. Fluid is coming in purely in the x direction, but it's leaving purely in the radial direction. Now there isn't going to be any radial reaction force here because just as much fluid is going to be deflecting up as down, as towards us, and as into the screen. So the fluid is deflected all the way around in the radial direction, so there's no net force produced by that. So we really only have to look at the x, or the horizontal component of this force. So we'll go back down and work just with the x component. So we'll rewrite this and say we're going to consider only the x direction. So in the x direction, this becomes reaction in the x direction. So this is the x component of the reaction. So we have an integral over the surface of density. Now, here's where I want to go back and look at the general equation. So notice we have a velocity here and a v dot n here. Well, the velocity is just this, because we're looking in the x direction, and that is purely in the x direction if we look at our diagram. So that's just in the x direction. So the velocity in this equation is just that in the x direction, and v dot n, as we found out when we looked at conservation of mass, is minus that. So when we write this down here, we take our velocity profile, which is center line velocity times 1 minus r over r, and that's squared. And there's a negative out front of here because of the v dot n. And then our element of area is r d theta, and so the limits are 0 to r and 0 to 2 pi. So now this is very similar to evaluating the integral for conservation of mass, but we got to remember this squared up here, so it's a little bit different. So the reaction, take out everything that's constant here, minus rho uc squared, so there's a centerline velocity there, which is squared, 2 pi, because we can evaluate the theta integral right away. Nothing in there depends on theta. And then our r is 0 to r, so we're integrating 1 minus r over r squared, so I'm just going to square that out. So that's r minus 2r squared over r plus r cubed over r squared. And remember, there's an r here as well that I've distributed into there, and dr. So that's equal to minus rho uc squared 2 pi r squared over 2 minus 2r cubed over 3r plus r to the 4th over 4r squared. That's going to be evaluated from 0 to r. So that's equal to negative 2 pi rho uc squared r squared times 1/2 minus 2/3 plus 1/4. So notice when you substitute in this r, there's an r squared. You can factor out every one of those terms. So this all evaluates to minus pi r squared rho uc squared over 6. So we're ready to substitute numbers into this. So we have minus pi, r is 0.05 meters squared, r squared is 0.05 squared meters squared. Density is 1,000 kilograms per meter cubed. The center line velocity we solve for up here, 1.528. So 1.528 squared, that will be meters squared per second squared, divided by 6. So that reaction works out to minus 3.06 newtons. So that's the reaction force. So remember, this is a force on the control volume. So let's go back up to our diagram and just see if this makes sense. So that's the force exerted on the control volume at this spot here where the strut is cut. So that's a force in the minus x direction. So that makes sense. So the fluid is smacking into this thing. So to hold it in place, we've got to exert a force in that direction. But this actually asked for the force exerted on the plate. So that's going to be the opposite of that. So we should do that down here. We should say, therefore, force on plate by water is 3.06 newtons. And that's in the I direction. So that's all good. Now, we were also asked what would happen if that inlet velocity had been uniform. So this had been a flat profile. So if the pipe exit had been uniform, so the same mass flow rate, just a flat velocity profile instead of that pointy one. Well, in that case, we could use the uniform flow assumption. So looking just at our x component, this would be the reaction in the x direction would be minus, because it's an inlet, m dot times the x component of velocity at that inlet. And so that would be equal to minus m dot, which we have, and the x component of velocity would be the mass flow rate divided by the density and the area of the inlet. So remember, mass flow rate is density times velocity times area. So that velocity would have to be mass flow rate divided by density and area. And it would be just a uniform value. So this we can evaluate. So this is minus 4 kilograms per second. That's our mass flow rate, but it needs to be squared, divided by the density, 1,000 kilograms per meter cubed, and divided by the area, which is pi times the radius, 5 centimeters squared, and that'll give us meters squared. So this reaction works out to negative 2.04 newtons, or less than we got up here. Remember, this was 3.06. And you'll notice it's 50% higher. So the force is 50% higher because of the non-uniform profile. So remember, the same conclusion would be made here. The force on plate would be positive 2.04 newtons in the I direction.